Welcome, congratulations.
Great. Thank you. Hi, everyone. Thanks so much for the kind introduction and for this honor. I'm really excited to be giving this talk. So today I'm going to be talking about GIGA-Lens, which is our fast differentiable Bayesian lens modeling framework that we've called GIGA-Lens. So before I get started, I just want to talk about the wonderful collaborators I've worked with from a variety of places, ranging from Lawrence Lab to NSF to Max Planck. So their input and their guidance has been really invaluable to me, and I just want to take a second to acknowledge their guidance. And I'd also like to thank, of course, the NERSC team for all their support and resources. Like, none of this would be possible without the support and the resources they provided. Okay, so what exactly is strong gravitational lensing? It's this phenomenon that's predicted by Einstein's general relativity, where there's a chance alignment between Earth, some foreground galaxy, and some background galaxy. So only 1 in 10,000 galaxies actually turn out to be gravitational lenses. So these are very rare phenomena. They're caused by this massive elliptical galaxy known as the lens. So the galaxy in between Earth and the source. It warps space-time to bend light from this background galaxy, which we call a source. And the bent light forms an image that's highly warped. And it typically makes large arcs and shows like multiple images. So on this slide, you can see 2 typical examples of a gravitational lens. So the one on top is a structure known as an Einstein ring, which occurs when there's like a high degree of circular symmetry, and the Earth, the lens, and the source are all almost perfectly collinear. So you get this like very ring-like circular structure. On the other hand, below we have something else called an Einstein cross. So this is another very generic or like common structure you see for gravitational lenses, where you have the lens galaxy sitting right in the middle, and then the 4 source galaxy, the 4 counter images of the source sitting outside. Okay, so aside from being interesting to look at, what are these lenses really good for in terms of like a scientific use case? Well, first of all, they can be used to test predictions of the lambda CDM model, which is a cosmological model that people generally have a strong degree of faith in. Particularly, they can characterize the nature of potential dark matter halos in which the lensing galaxy is embedded, or even halos on the line of sight between us and the source. Second, they can be used to infer the Hubble constant, which is an extremely important constant in astrophysics, in the case that a multiply lensed supernova explodes behind the lensing galaxy. This is because the 2 images will actually appear to explode at different times, and we can use this delay or this time difference to infer the Hubble constant. Finally, when multiple different sources are lensed, these systems can also be further used as a probe for cosmology and dark energy, especially at high redshifts. Okay, so before I get into the lens modeling framework and the work that we did, I think it makes sense to give a little bit of an overview of the basic mathematics and physics behind gravitational lensing. So I'm just going to try to give you a high-level understanding of what's going on. So the central equation here is really known as the lensing equation, which I've written on the slide, and it expresses a fairly simple geometric fact, which I've illustrated in the diagram. So here, the S in the diagram marks the source, the disk, the circular thing in the middle marks the lens, and the O marks the observer, which is us, or Earth. And theta is the angle at which we see the image. And alpha in this diagram is this quantity known as the deflection angle, because it basically measures how much the light from the source has been bent by the lensing galaxy. So for different types of galaxies, the functional form of alpha may differ depending on the mass distribution. And since it turns out that dark matter consists of a large fraction of the mass in a galaxy, the typical number is something like 80%, that's why modeling lensing can help us understand dark matter, because dark matter is believed to really dominate this lensing effect. So with all that aside, like the simplest archetypical lens model is known as a singular isothermal sphere. This is basically where one assumes that all the stars in the galaxy can be modeled or described as free atoms in a gas of uniform temperature. And for systems belonging to this class of lens, the deflection angle is actually analytically expressible. It's very simple. It's actually just a constant. So this constant is known as the Einstein radius, and it's a parameter that depends on the mass and the redshift of the lens, so the distance of the lens from us. The reason that this is called a radius is that if a source sits perfectly behind the lens, then the image that will be formed will have a radius that's exactly equal to the Einstein radius. So with the lensing equation, it's actually quite easy, I guess, conceptually to simulate lensing, because if we know the parameters of the source and the lens, then we can compute the deflection angle. Hence, we can compute the image. So this is known as the forward problem because we're kind of going in the forward direction from the ground truth to observables. The image on the right is an instance of a simulated lens where I pretend I know the ground truth parameters for the source and the lens, and then we basically try to simulate it with realistic observing conditions. So there's noise and there's effects from the telescope, et cetera, et cetera. So although it's not perfectly symmetric, I've roughly indicated the Einstein radius on the figure, which gives an order of magnitude for what the Einstein radius of this lens is. Okay, so now what is our problem? Well, our problem is pretty typical, which is that we don't have access to the ground truth parameters. We only have the observable, which is typically just a noisy image of the lensing system. So to move towards our science goals that we mentioned on previous slides, so such as dark matter testing or Hubble constant inference, we need the ability to do several things. So using the observed image, we want to learn about the light profile of the source galaxy. We also want to learn about the distribution of matter in the lensing galaxy, and potentially even dark matter halos near the lens or along the line of sight. To maybe put it another way, in the language of Bayesian statistics, what we actually have is an inference problem, right? So as you might anticipate, we'll be making quite extensive use of the Bayes equation, which just expresses the posterior distribution of the parameters as a product of the likelihood and prior. But I just want to note, you might catch me slipping into like a more physics language and just calling this problem modeling, but modeling and inference will refer to the same thing. Okay, so I'm going to describe a high-level strategy for like how we're going to tackle this inference problem. So the first thing that we need to do is write down some sort of model for the physics. So this includes a functional form for the source and the lens light, as well as the lens mass. This mass model is actually always translated into a deflection angle, and that's what we use in practice for the modeling. But yeah, so the next step is then to write down a model for the probability. What that really means is we need to find a prior for the parameters as well as the likelihood. So the likelihood typically will assume that the noise at each pixel in the image is Gaussian. So the log likelihood really just looks like a squared error or a chi-squared up to some multiplicative factors. So speaking loosely, all we're trying to do is match the simulated image to the observed image. And this matching is measured by a squared error. And all the Bayesian formalism does is to kind of make this rigorous and calculate and to characterize the uncertainty for the parameters after we've done our fit, basically. So once we've written down a physical and a probabilistic model, we're pretty much ready to sample from the posterior, which seems simple enough. The problem is this: when we start looking at how to sample, we're faced with a number of hard problems. Well, the main one is that most regions of a high dimensional parameter space have a vanishing likelihood. So if we use some out-of-the-box Monte Carlo sampler like MCMC, we're likely to waste a lot of time in regions of the parameter space that we really shouldn't be looking at because they have vanishing likelihood. So our solution, which is an approach first introduced to us by another open source package, it's called Lenstronomy, is we essentially look for the global maximum of the posterior density first. And if we can find that, then, and also assuming the posterior is unimodal, which is something I'll talk about later, but assuming it's unimodal in the sense that like all the other local maxima of the posterior have very low likelihood anyways, then we can just initialize our sampler at this point of high posterior density and it'll do much better. So this actually leads to another problem, which is how do we identify the global maximum? Because the parameter space is highly non-convex and therefore is hard to search over, right? So the figure on this slide kind of roughly illustrates that problem, which is that when you have a non-convex loss function or a non-convex loss landscape, which is in our case the posterior density, depending on where you start, you'll end up with different solutions of varying quality. And it's hard to determine, whether or not you found the global maximum. Okay, so with these, with our goals and these problems in mind, then we had three main desideratum when we were trying to come up with a new lensing package. The first was that we required fast simulation. So as I kind of hinted at, simulation is a key to forward modeling. And if you want a fast inference code, then you need a fast simulation code. Luckily, most popular lens models are analytic. So their deflection angles can be calculated via a series of simple matrix operations. And this is what I mean by the lens models are linear algebraic, right? So since this is the case, we can actually use GPUs for fast simulation because we know GPUs are exceptionally good at elementary operations on large matrices. So next, we need some way to guide us through high dimensional parameter spaces. I'll make the case that without some guide, known as zeroth order methods, modeling can be very inefficient. So we found like zeroth order methods to be an issue because there's virtually no performance guarantees associated with these, and convergence can be very, very slow. So what we've chosen here is we've made our guide of local one. So specifically, we've chosen the gradient. This is actually particularly fitting because, as I mentioned previously, lens models are analytic and therefore they're differentiable. So we can easily access the gradient via automatic differentiation, which is a technology that's now widely available in most linear algebra libraries. So finally, we want a robust framework, which means that it produces consistent results across many different runs. So it doesn't fail often, and it also doesn't require us to carefully tune the initialization to get the right answer. So our approach is pretty simple. We hedge our bets, basically. So as a general design principle, we'll use many candidate solutions whenever possible. So the failure probability will vanish very quickly with the number of candidates we use. So I'll try to elaborate on that further in coming slides. But to maintain many candidate solutions, we'll use parallel computation with GPUs. Okay, so this is why we developed our framework, which is known as GIGA-Lens, standing for a gradient-informed and GPU-accelerated lens modeling framework. We wrote this library with these three desideratum in mind, and as some of you may have realized, the popular TensorFlow is a really good choice for most of the features that we wanted. So our code is fully vectorized and fully differentiable using TensorFlow's autodiff, and it also runs natively on GPUs. So furthermore, we actually wrote a parallel branch in JAX that has further support for distributed computing using multiple GPUs, which we were conveniently able to test out on the new Perlmutter system. So we should also note that we use another library called TensorFlow Probability, which is very useful for some of these like Bayesian modeling primitives. Okay. Great. Okay, so now to get down to the actual modeling procedure used in this library. So as I mentioned before, our strategy is to first identify the global maximum of the posterior density, and then to use this to inform how we initialize our sampler. So we do this with multi-starts gradient descent, so what that means is we'll initialize many different candidate solutions by just sampling from our prior. This prior should be broad enough to include the global maximum. And then next, we'll use a bijector to unconstrain various parameters in our lens model. I know that might sound kind of confusing, but to make it concrete, let's take the Einstein radius. So since this is a radius, it should always be positive, but it's undesirable to like manually constrain the parameter to always be positive in our gradient descent. Like these kind of hard walls are not very natural. So what we do is we use bijectors that map parameters into an unconstrained space and then optimize in that unconstrained space. So for the Einstein radius, what that means is we just take the log of the Einstein radius and optimize over that, and that can be unconstrained. The next thing that we do is we localize each individual candidate solution using gradient descent with respect to the posterior density. We'll typically use Atom with an annealed learning rate, which is pretty typical setup for non-convex optimization problems. And then finally, after a number of iterations, we'll stop and select the best performing solution and use this as the maximum a posteriori estimate. Okay, so how well does this actually work in practice? Let's look at an example system. On the left, I've shown the trajectory for two parameters, or specifically the error trajectory of two parameters with respect to time or the number of gradient descent iterations. The solutions that have been bolded are the ones that converge to the correct solution. So you'll note that the failure probability seems to be pretty high. Like it looks like, for each individual particle, the failure probability is roughly 96% is what we actually found here. In the test we did for our paper, we found a roughly 98% upper bound on the failure probability. But when you aggregate this across 300 or 500 candidate solutions, then the failure probability becomes vanishingly low because at least one of those particles with high probability is going to find the correct solution, basically. So on the right, I've shown the loss trajectory for the best performing 6 candidate solutions over time. And you'll see that by the 300th iteration, roughly, the particles seem to have come into the neighborhood of the optimum, because after this, they exhibit a very smooth geometric convergence, which is characteristic of loss trajectories in convex regions of the loss function. So they've kind of reached the basin around the global optimum. So this is actually what informs our cutoff for the number of iterations that we use in gradient descent. Okay, so before sampling, we still have one more important auxiliary step, which is that we want to estimate the covariance, which will be important later. So we find this estimate by using a technique known as variational inference. This procedure is essentially one where you fit an ansatz distribution, which I'll call our surrogate posterior, to the true posterior. So if we take a look at the diagram, let's say our true posterior is this funny looking object like the one in blue that we don't really have a good handle of. And if we want to find a rough characterization of it, we might use a simpler analytic distribution indicated by QZ, it's in green, and try to fit this distribution to the ground truth distribution. So the fit or the degree of agreement between these two distributions is measured by the KL divergence between the two. So for us, since we want the covariance, we're going to make our ansatz or our surrogate a multivariate normal, and then basically try to fit the covariance and the mean to the underlying posterior. Okay, so it turns out that the KL divergence up to an additive constant can be written as something else known as an evidence lower bound. It looks kind of messy, but all it is really just an expectation of a difference in log densities. So the gradient is actually similarly expressible. I'm not going to go into the details, but yeah, there's very simple Monte Carlo estimates for both of these quantities, right? So to optimize the KL, what we're going to do is the following, right? So we initialize the mean of our surrogate posterior at the MAP estimate from the previous gradient descent step. The next thing that we do is we minimize the elbow or the evidence lower bound by approximating the two expressions, the elbow and the gradient of the elbow, using Monte Carlo estimates. So what that really means is we sample many different thetas from our surrogate posterior, we calculate some gradients, average, and then update our gradient descent. And then finally, after we've minimized our KL, the final optimized covariance matrix is an estimate for the true covariance. So if you want a frequentist interpretation of what we're doing here, this can kind of be understood as taking the Hessian of the log posterior at the mode. And this actually works pretty well, just as well as VI in low dimensional parameter spaces. But in high dimensions, we find that the Hessian becomes unstable, and then VI is significantly more reliable. Okay, so finally, we're prepared to sample. Since we have gradient information natively with GIGA-Lens, we can take advantage of this to use a sampling technique known as Hamiltonian Monte Carlo. So this is a sampler that was proposed to handle the inefficiency of MCMC in high dimensions. If you want to understand like what this inefficiency comes from, it originates in this idea of a typical set. So when we're sampling, we really want to spend most of our time in this area known as a typical set. And in high dimensions, the space can be highly non-trivial. It can have a very funny structure. So just like some sort of diagram, it could be like this, that you can think of it in this way. And while MCMC will make lots of rejected proposals that exit this typical set, HMC is able to use gradient information to just smoothly follow the curvature of the typical set, basically. And you get very efficient sampling in this way. So, Hamiltonian Monte Carlo is not a perfect sampler. It requires some hyperparameters and an initialization configuration. So most importantly, we'll have to set a parameter known as the mass matrix to be the inverse of the covariance matrix from VI. So this is really to give you some intuition. The purpose of this is to inform the sampler of the various scales associated with each parameter. And these things can vary significantly for our problem, right? Like some parameters could have a variance of 10 to the minus 3, and some could have a variance of 1. So these vastly different scales, HMC does not handle that well, or this like anisotropy well, without being given a mass matrix. So once you give it this mass matrix, then HMC is basically able to adapt to that. Other hyperparameters for HMC are just adaptively tuned over the burn-in phase. Okay, so to give you an idea of the performance improvements we're able to extract with HMC, I'll compare it to another popular ensemble sampler in astrophysics known as EMC, which performs very similar to MCMC. So you can roughly think of the two as the same. But let's take a look at the trace plots for just one critical parameter, which is the Einstein radius. We see that every single iteration, HMC is drawing pretty much an independent sample, which is ideal behavior. Whereas for EMC, we get highly correlated behavior, and it seems like it takes many different iterations before we get a new independent sample. So this idea can be kind of quantified with metrics like the effective sample size, which measures the number of independent samples drawn in a sampler. And you see that HMC is able to do several orders of magnitude better than EMC in terms of effective sample size. Okay, so with that, that kind of completes our modeling pipeline. Once HMC is done sampling, we've drawn many samples from the posterior, and then we can do inference. So I've shown on this slide modeling results for one typical system, which is very close to a perfect Einstein ring. The corner plot on the left shows the distribution of HMC samples as well as the VI posterior. So interestingly, we can see that variational inference did a pretty good job of capturing the typical scales of the posterior. So observe the scale of the Einstein radius is 10 to the minus 3. And for gamma, the parameter on the right, the scale is almost 0.1. So very, very different scales here, differing by almost 2 orders of magnitude. And VI is able to actually correctly identify that. So however, it's not perfect, obviously, because we found that our posterior itself is not perfectly Gaussian, despite how the marginal distribution might appear. So for instance, to illustrate this, we looked at a random 2-dimensional cross-section of our posterior and found non-Gaussianity in the HMC samples, which is shown right over here. Whereas, of course, the variational inference is Gaussian. So on the right, I've shown some diagnostics for just basic timings. On the right, I've shown some diagnostics which have the observed image, the reconstructed image, as well as the residual of the two. So you can see we get almost a perfect reconstruction, and the residual is basically just noise. And the execution time in total is just over 100 seconds on 4 A100 GPUs with Perlmutter. So as you can see, variational inference is actually the most costly step, which is something we'll be trying to address in the future. Okay, so to verify the correctness of our modeling code, the last thing that we did is we simulated 100 random systems, completely blinded, and just modeled all of them, and then compared basically what our pipeline inferred with the actual ground truth. And we found no bias as well as well-calibrated uncertainties. So as in the mean chi-squared for each of these was close to 1. This was like a pretty important test in both the speed and the robustness of our code. Okay, so I think finally, I'm excited to show modeling results on a real observed system. So this is a system that we observed with the Hubble Space Telescope. What we have here is a pretty classical lens in terms of the geometry. So we have a quad, so that's highlighted in the orange. And then we have a double, which is highlighted in the white. So we have 2 sources being lensed, making this a very interesting system. And we see that GIGA-Lens did pretty well modeling this system. So we get a chi-squared of roughly 1, basically. Okay, great. So for next steps, our paper reporting on these results was published to arXiv and also has been accepted for publication in the Astrophysical Journal. what to do next? Well, the next steps that we're considering are whether or not we can actually improve speed by, I mean, we assume that we will be able to improve speed, but whether or not we can get our code to run with 2 GPU nodes. So this would mean 8 GPUs on Perlmutter, which is an exciting prospect for us. And another question is, could we eliminate the VI step, which is the most costly step, by using mass matrix adaptation for HMC? And in terms of science goals, we want to start applying our modeling code to more real observed data from the Hubble Space Telescope. So yeah, that wraps up my talk. Thank you for listening, and I'd be happy to take any questions.
Oh, great. Thank you, Andy. Great talk. Do we have any questions? Well, I guess I'll start with one. So, you laid out at the beginning some of the things you'd like to be able to do with the work on gravitational lenses, one of which was determine the form of the lensing distribution of matter.
Yes.
And so where are you with being able to make statements or draw conclusions about that?
Sure. That's a great question. So as soon as you get into like questions of you want to determine the form, you really have to introduce many more parameters to kind of model that uncertainty in the form, which is something that kind of this modeling framework was written to address. Like it was written to work well in high dimensional parameter spaces. So that's currently a work in progress. So I guess I can't say anything about that yet, so we don't have results, but it's something that we're thinking about.
Okay, all right, thanks. Other questions? So I guess I have one for you. I see that you're now pursuing a degree in quantum science or quantum information science. Are you continuing to work on this project, or what is the? What is your focus these days?
So I think I'm definitely focusing more on the quantum side of things. I think for this project, I've taken on more of like a maintainer role, and I kind of I guess meet with the team once every month or once every 2 weeks, just to discuss future directions. But in terms of like actually active technical work, I think I've taken a step back. But yeah.
Okay, interesting.
So yeah, we meet with Andy once every, as Andy said, 1 to 2 months, and as we pursue actual real systems to model, and we're also getting spectral data needed to. So what Andy has done with this framework is without the distance information, it's all geometrical, and so now we're getting redshift information, which would allow us to actually measure the distance to the lens of the background source, and then we can actually get the physical parameters. That's the next step, and Andy's helping us with that. Cool.
So is James Webb offering new opportunities for you in this space?
Yeah, we'll probably be proposing in the next cycle. But meanwhile, DESI and the other spectroscopic DESI, which is also processing its data on NERSC, is giving us spectroscopic data so that we can model our Hubble systems.
Okay, great. Okay, well, thank you. If there aren't any other questions, I want to thank all of our speakers today. This was really very interesting, and I know I really enjoyed it. So thank you, and best wishes, and keep letting us know interesting things that you're doing in the future. So thanks, everybody.
Great. Thank you.
Thank you very much.